Okay, here we go. This is problem 7 from your worksheet. Again, it's not in the book, but this is definitely something we need to learn how to do. What we're going to be doing here is finding the center of mass of a thin rod with non-uniform density. All right, and so you're given the linear density. You're given the linear density of the shape, and you're told specifically that it is that. Right. So remember, when we talk about linear density, we're talking about the mass per unit length of that shape. Okay. Now, to find the center of mass, remember what we learned was that you had to integrate the position with respect to the mass and divide that by the total mass of the thing. Okay. Now, so because you're integrating with respect to mass, in this integral, our bounds of integration are from 0, a mass of 0, until we get to the total mass of the thing. So capital M here represents the total mass of the shape. Okay. Now the problem here is we don't know the total mass, right? So what we learned in class was that you could find that total mass. So the top of this integral is going to stay the same. We're going to integrate from 0 to capital M, the position with respect to the mass. And kind of a trick, this is basically a result of the fundamental theorem of calculus, is to find this total mass, we can simply integrate from 0 to total M, the mass, with respect to the mass, I guess I should say. Okay? So question A says to find the mass, so that's basically just the bottom of this fraction here. Okay? That's going to be question A. But in order to do that, we need to figure out how to take this integral. We got to figure out what dm is. And so in order to do that, we're going to kind of do a little trick here. And this is always, with these linear density problems, this is how it always works. All right, what I'm going to do is I'm going to start with that expression. I know that lambda is the mass per unit length. So if I algebraify this, if I multiply both sides by dx, I find that dm is lambda dx. Oh, but look, lambda is this expression in terms of x. So now I can do dm is 0.3 x squared dx, right? Just by replacing lambda with this expression up here. Okay? So, here we go. Let's do the bottom part of the fraction first. Okay, so what I'm going to do is we're going to do part A, which is, again, this integral. So part A. To find the total mass, I'm going to integrate from 0 to total mass m, dm. That's the same as integrating dm, well, that's this mass. So 0.3 x squared dx. But now I'm no longer integrating with respect to mass. I'm now integrating with respect to position. Well, the problem tells me the length of my rod. So if it starts at a position of 0, it's going to end at a position of 1.2 meters. Okay, so now I'm just going to integrate this mess. So let's see. I want to integrate 0.3 x squared. So again, the question is, what do I integrate? I'm sorry, what do I take the derivative of to get this mess? Well, let's see. I need x cubed. And when I bring the 3 down, I got to multiply something to get 0.3. And I know that 0 times 0.1, sorry, 3 times 0.1 gives me 0.3. So I think that this works, right? If you take the derivative of this, you're going to get this expression. Okay? And then my bounds of integration are from 0 to 1.2. So I'm going to simply put 1.2 in here and put 0 in here, and then find the difference. So this is 0.1 times 1.2 cubed, and then minus 0. Okay, so what do we get? Okay, so if we get that, sorry, I had to go grab a calculator, it gives you 0.1728. Gives you 0.1728 what? Kilograms, right? Because we're talking about mass here. Okay, so that's part A. Now, to do part B, now we've got to do this whole integral here, right? This mess. So fortunately, we've already done the bottom. So really all we got to do for part B is do the top and then simply divide, right? So to do part B, I'm going to integrate from 0 to m x dm and then divide it by this answer that I got before. So the integral from 0 to m of x dm is x, the integral of x times dm. So that's this again, right? So 0.3 x squared dx And again, my bounds of integration change. Instead of going from 0 to m, I'm going to go from 0 to 1.2 meters. Okay? So this is the integral from 0 to 1.2 meters of 0.3 x cubed dx, which is, let's see, what are we going to get? We're going to get x to the fourth, and I'm just going to write 0.3 over 4, right? So that when you multiply by 4, the 4's cancel, right? So from 0 to 1.2. So grab your calculatrix and figure out what you get there. So if you do that, that gives you 0, oops, my pen keeps doing this to me. Gives you 0.15552. So, see if I can minimize that, yeah. So that means then that our center of mass is going to be 0.15552, and this is actually kilogram, what were our units? Kilogram meters, divided by 0.1728 kilograms, and it gives you exactly 0.9 meters. All right, so that is that. So finally, part C. Let me clear up the screen here a little bit. Okay, so now we're basically going to go back and do the same thing again, but we're replacing this 0.3x squared. Oops, we're replacing the 0.3x squared with just kx squared, right? So here we go. So here's what I know. I know that my linear density is the amount of mass per unit length, which means that dm is lambda dx. This is a lambda here. And so lambda is kx squared. So this is kx squared dx. So my position of my center of mass is the integral from 0 to m of x dm over the integral from 0 to m dm, right? So this is the integral of, so remember, this is my dm, right? So this is x times kx squared dx from 0 to L, right, because we're looking at a rod of length L instead of 1.2 meters, over, same thing, down here, our dm, so it's the integral of dm, which is this kx squared dx, and to get our total mass, we've got to integrate from a position of 0 to a position of L. So, let's see, I'm going to get the integral from 0 to L of x times x squared is x cubed. I can pull this k out, right? You don't have to, but it certainly simplifies things. Over, same thing on the bottom. I'm going to pull the k out and go integral of 0 to L x squared dx. Ooh, this doesn't look like it's going to be too bad. Let's see, my k's cancel out. K's cancel. And let's see, the integral of x cubed, well, that's 1/4 x to the 4th, right? From 0 to L. Over on the bottom, the integral of x squared, that's 1/3 x cubed from 0 to L, which then becomes 1/4 of L to the 4th over 1/3 of L cubed. Oh, let's see, I've got 4 L's on the bottom and 3 L's on the bottom. Did I say that wrong? 4 L's on top, 3 L's on the bottom. So now I'm looking at 1/4 of L over 1/3. So multiply by 3, you get 3/4 L. Okay, so there you go.